A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about material derivative. So let us get started. So the only topic for today's discussion will be the material derivative. It's a very important topic and sometimes one of the most confusing topics for students in this course. So please pay attention as we go through the discussion in this lecture. We will first talk about the meaning of material derivative, write the equation for this in both the Lagrangian and Eulerian forms, and then towards the end, I'll show you a mathematical proof to give you confidence in the expression for the material derivative. So let's begin. So material or total derivative is defined as the time rate change of a property if the observer who is doing the measurement is attached or sitting on the particle while measuring the change of the property. It is called a material derivative because the observer who's making the observation is attached to the material particle while measuring the change. This is very important because the observer must be sitting on the particle while doing the measurement, and that is called material derivative. So let us say we are measuring theta, which is the temperature, and theta is described in the Lagrangian form. So if you're talking about the material derivative of theta in this case, that is d theta by dt, where theta is described in the Lagrangian description, this simply will be given as the partial derivative of theta with respect to time, and this is because capital X, that is the material coordinates, do not depend on time. So if I was interested to measure the time rate change of temperature for a particle P in the body, I'll put superscript P here. So that means that I pass in the material coordinates of the particle P into this function and then I differentiate. So this gives me the change in temperature for the particle P as a function of time for a given time value. Of course, as time evolves, the derivative d theta by dt will also change. So this is a function of time. But we'll keep the definition more general. So in the Lagrangian description of theta, the material derivative d theta by dt is simply partial theta by partial time. In many texts, you will notice that material derivative is also written as capital D by capital T of theta in this case. So that also refers to the material derivative. Now, in many situations, it is more intuitive to define the quantity, that is theta in this case, using its Eulerian description. So let us say theta is described in the Eulerian description, and now we are interested to find the material derivative of theta in this Eulerian description. Now the material derivative is still having the same definition, that is, it is the change in temperature with time while the observer is sitting on a material particle. Just because we have described theta in the Eulerian form does not change the definition of material derivative. It is still the same thing. Now, mathematically speaking, we can apply the chain rule here. So this becomes del theta by del time plus del theta by del x1 times dx1 by dt plus partial theta by partial x2 dx2 by dt and del theta by del x3 times dx3 by dt. In the initial form, I can write it more simply as partial theta by partial xk times dxk by dt. Now, just to show that theta is written in the Eulerian description, I'll write it like this: partial theta by partial t, where theta is in the Eulerian description, plus partial theta by partial xk. Again, theta is a function of small x in t times d by dt of xk. Now, this quantity that we have here is called the local rate of change, and this quantity here is called the convective rate of change. Now, if we look at these terms, that is this one, this is dxk by dt, which simply is the velocity. So this is due to the flow of the material. And the other part, which is this one, shows the gradient of theta, which is telling us that theta changing as a function of spatial coordinates. That is, the temperature varying with spatial coordinates. So this is the temperature gradient. So let us understand this from an example. So let us say we have a swimming pool and there's some water in the pool, and there's sun that heats the water in the pool. Now in case A, there's no flow in the pool. So if I'm measuring d theta by dt, which basically is the material derivative of temperature for a particle P, since there is no flow, so the particle P will stay stationary. So it is as if you had put in a probe at that location where the particle P is sitting and measured its temperature. So this will be purely equal to partial theta by partial t. So this partial theta by partial t means that you keep all other coordinates, that is small x1, small x2 and small x3 constant. So when the spatial coordinates are constant, it's as if you are measuring the quantity by fixing a probe in some spatial location. So as sun heats the water, we will notice the temperature of water at all points in the pool changing with time, and this is what will be measured as the material derivative in this case. So this is a purely local rate of change. Now we take another case, and in this case the water on the left part of the pool is cold and water on the right part is hot. I'm not telling you why this is the case. We'll take it for a given. And also there's some flow happening from left to right. And let us say that there is no sun right now. So if I fix a point, let's say point F, which is a fixed point, so it's a point in the spatial coordinates, and I measure the local change of temperature with time for this spatially fixed point F, I will notice that this is 0. And that is because at that spatial point F, there is no temperature change with time. So it was the sun's radiative heating earlier that was causing the temperature of the water to change with time locally. But now, since there is no sun, so the water temperature does not increase with time at any fixed point in the pool. So now if I talk about a particle P, it's a material particle, and we measure the material derivative of theta. That is, we sit on the particle P and measure the change in temperature. That will be a positive quantity this time, because at one instance I measured the temperature here where the particle was here. So I measured the temperature that was cold, but as the particle moved slightly, let's say, now it moved to a hot region because remember there is a spatial gradient of temperature this time in the pool. So as the particle moves to the hotter region in the pool, you measure a higher temperature. So you see that d theta by dt, that's a material derivative, is positive. And this contribution is purely because of the movement of particle, that is because of the flow in the swimming pool. So as we saw in the convective part, this was a product of partial theta by partial x, which was the gradient, and the velocity component. So in this case, the velocity is positive, that is from left to right, and the gradient is also positive because the temperatures on the right are higher than those on the left. So we can see that the product is also going to be positive. So in this situation, we have a purely convective rate of change and no local rate of change. So the convective rate of change requires two things. One is the velocity and the other is the temperature gradient. So in case there is no velocity, that is v is equal to 0, then even if there's a temperature gradient, we will not measure any material derivative because the particle will not move with time. So it's still sitting on the same position in space. So it still measures the same temperature with time. Remember, there's no local rate of change right now. And if, on the other hand, del theta by del x is 0, then even if there is a velocity, the particle moves in the same temperature region. So the final temperature is the same as the initial temperature. So there is no change measured by the observer. So I'm giving you a very intuitive understanding of the material derivative in this case. Now generally, we'll have contributions from both the local and the convective rate of change. So this was purely for the sake of intuition. I gave you two extreme cases where in case A, there was only a pure local rate of change, and in case B, there was purely a convective rate of change. Now, many a times people have confusion as to what is the motivation of studying material derivative in this course. Now, in mechanics, we work with Newton's laws, especially the Newton's second law. So, Newton's second law states that the force acting on a material particle, let's say this, is given as the time rate of change of the momentum of the particle. That's one way to write this law. Now, there may be situations where expressing the momentum of the particle is more intuitive in the Eulerian form. So, even then, Newton's second law is still valid when applied to a material particle or a collection of material particles. Newton's law does not care about our choice of the description of the quantities. So when we have to apply Newton's law to a particle that may be moving, let us say, we will have to measure the time rate change of the momentum of the particle by sitting on the particle. So what that means is that we have to measure the material derivative in this case. Now, since the momentum is given in the Eulerian description, so we have to use the material derivative, which is dp by dt as a function of small x and t is partial p by partial t plus partial p by partial x k times dxk by dt. So this is one of the major motivations of the material derivative. So coming back to the discussion on material derivative, we can write the material derivative of a quantity which may be an nth order tensor expressed in the Eulerian description as partial by partial t of pijk dot 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 plus partial by partial xk of pijk dot 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 times vk. So I've written dxk by dt as vk because that is the definition of the velocity vector. So in general, in the operator form, I can write this as d by dt of a quantity expressed in the Eulerian form is partial by partial t of the quantity plus vk times partial by partial xk of the quantity. Or in the symbolic notation, I can write this as the velocity vector v dotted with a gradient of the quantity. I must write that we are using an Eulerian description as this description may be more intuitive in certain situations. It is especially in fluids that we tend to use this material derivative because in situations when we deal with fluids, we are more interested to measure quantities at certain specific spatial locations, or we describe quantities in their Eulerian description. For example, density may be written as small x vector comma t. So I'm measuring the density at a given point in space which is fixed in my room coordinates. But remember, Newton's second law does not care about our choice of coordinates. It is still valid on a collection of fluid particles. So when writing the momentum equation for fluids, and we'll do that later in the course, we will still use the external force acting on a collection of fluid particles is its material derivative of the momentum. So since momentum, which is mass times velocity, is expressed in the Eulerian description, we'll have to apply this form of the material derivative. So we'll do that rigorously later. So now that we have an expression for the material derivative, let us prove it to get a better appreciation for this quantity. We will not solve any problem today. We'll be solving problems on this topic in the tutorial to come. But today we will show you a proof of why it is the case that the material derivative is sum of the local rate of change and the convective rate of change. So this is the question we have, that why is it the case that the change that is measured by sitting on a particle, which is the material derivative, the same as the sum of the local rate of change and the convective rate of change. Now using the chain rule is okay, but we must show that why is it the case that this sum, which is d theta by dt, actually denotes the time rate of change of the quantity when measured by sitting on the particle. Because this is the confusion that many of us have in the beginning, that we are not able to reconcile the mathematical expression here with the physical meaning of the quantity, that is, the quantity measured by sitting on a material particle, or more specifically, the time rate of change of theta measured by sitting on a particle. So we'll prove it for a 1D situation because mathematically it is easier to show that for a 1D situation, but with the same ideas you can show it for 2D or a full spatially 3D case. So for our case, small x is some function of capital X in t. So this is our chi function, and theta is a function of small x in t, which is in the Eulerian form. But if I use the Lagrangian form, that is, if I use capital X in t, that gives me the Lagrangian form. And we'll say that these are equal in the sense that, let's say this is a particle P at time t, and then as time proceeds, the particle P moves here, we call it P prime, at a time which is t plus delta t. So when I measure the temperature here, that will be temperature theta of capital X for particle P, comma t, and this is also the same as theta measured at this location small x. So this is the small x location, spatially speaking, comma t. And when the particle moves to P prime, we will say that this is theta of the same particle xp measured at time t plus delta t, because the particle has moved to P prime, and this is the same as theta. Now since the particle has moved, its spatial coordinate has changed as well. So theta at x plus delta x at a later time, that is t plus delta t. So as we can see here, that theta capital X comma t is equal to theta small x comma t for the coordinates we have chosen. We will now start with the intuitive definition of material derivative. So material derivative is the change in theta with respect to time when measured by sitting on the material particle. So if I use the Lagrangian description of theta, this is very intuitive. Let's write it down. So this derivative is the limit delta t tending to 0, temperature of some capital X, let's say this corresponds to the particle P, at a later time, minus the temperature of the same particle with a capital X at the earlier time, divided by delta t. So you can see this is the material derivative because we are sitting on the same material particle and measuring the change in theta. Change because first we measure the temperature at time t, and then we measure the temperature at time t plus delta t. So I'll write it down that this is by the definition of material derivative. So understanding material derivative when quantities are expressed in their Lagrangian description is very intuitive, because that is what the derivative says, that you sit on a material particle and measure the change. So this is going to be our starting point. So as we can see from the figure above, that theta for the particle capital X at t plus delta t can also be written as theta at the location small x plus delta x at the time t plus delta t. So I'll replace that here. So this becomes theta small x plus delta x comma t plus delta t minus a theta. Now a theta capital X comma t, which is this one from the figure above, is the same as small x comma t. So I'll write that down. And now you can see that we have written this in the Eulerian description now. So from now onwards, it is just some simple algebra. So what we'll do now is we will add and subtract the quantity theta x comma t plus delta t. So we'll take these two together. So this becomes limit delta t tend to 0 Additionally, what I'll do is, and I'll do that in the expression here, that I'll multiply this by delta x and divide by delta x. In fact, I'll move this delta t here and this delta x here. So this becomes limit delta t tend to 0, and then we have a theta x plus delta x comma t plus delta t minus theta x comma t plus delta t upon delta x times delta x upon delta t. And then we have the second term as well. Now we'll apply the limit. So let's look at the first term. So when you apply the limit, this basically becomes partial theta by partial x, and delta x upon delta t becomes dx by dt. And now if you look at the second term, this actually is partial theta by partial time, which is exactly what we are looking for. So this is the convective rate of change, and this is the local rate of change. So we have finally showed that the material derivative is the sum of convective and local rates of change. And we have shown it mathematically that the change in quantity that you measure by sitting on a material particle is the same as the sum of its convective and local changes. So I hope that you were able to understand the meaning of material derivative and also understand the expression of material derivative written for the situation when the quantities are expressed in their Eulerian description. We'll reinforce this understanding in the coming tutorial when we solve problems with material derivative. So thank you very much, and I'll see you in the tutorial next.